indeed a breakthrough in data organization, for they allow us to implement a host of algorithms much faster than when using linear data structures such as stacks, list, queue, linked list arrays. So the meaning of this point is whenever you want to insert the data or delete the data or access the existing data element using the data structures, the nonlinear data structures like trees take very less time compared to the linear data structures like stacks, queues, and linked list. Tree also provide a natural organization for data and consequently have become important structure in the file system, graphical user interfaces, databases, websites, and many other computer systems. Majorly, the tree is used to organize the data in the hierarchical manner, like our file system. Nothing but a simple example is suppose if you want to save your files in your computer, you may use folders, right? So you may use the folders like, for example, if you want to store any MP3 files, you may create a music folder. In that, you may create old songs, new songs. And in the new songs, you may store new songs. In the old songs folder, you may store old songs. Like that in the hierarchy manner, top level music, next level, new and old songs, and so on. So like that, if you want to arrange your data in the hierarchical manner, the trees is best suitable data structures. When we say that trees are non-linear, we are referring to organizational. The meaning of this point is generally in the linear data structures, we use links, two links, previous data and next data. That's it. We can any point of time, we can traverse either in forward direction or in backward direction. Just like next page, previous page only. But we cannot go to 50th page, 20th page, or starting point and so on. Directly we cannot jump. But coming to the trees, we can do that. That is what relationship organizational word means. It is used to represent the data in the hierarchical manner, with the objects being above and some objects are below of the some objects. We have one objects, some objects are exist above that object, some objects are exist below that objects. Better example to understand the trees, parent-child relationship. You can assume that a family tree. Let me start a family tree with grandfather, grandmother, next level, parents, next level, you, next level, your children, and so on. So this is what above and below relations, hierarchical relation. A tree can be defined in several ways. We have different definitions for the trees. One natural way to define a tree is a collection of nodes where a node contains a data. A tree is a collection of the nodes and the collection can be empty also. So without nodes, zero nodes also that can be treated as a tree. A tree contains zero or more nodes, zero or n number of the nodes. Otherwise, a tree consists of a distinguished node called the root node. In the tree, we have a root node. A root node is nothing but starting node with which you start the tree. that is called root node. As per our example, grandfather is a starting node. That is root node. I will show you that structure later on. And zero or more non-empty trees. We have one root node. We have another nodes, and that nodes contain non-empty nodes. Nothing but that nodes also contain another nodes, non-empty. And each of these roots are connected by a directed edge from the R. So these non-empty roots, non-empty nodes are connected with the root node with the edges. So this is also we may consider as another definition. The root of each subtree is said to be a child of the root node. The root of the subtree is a child for the main root. And R is the parent of each subtree. So we have two subtrees, let us say. So R is the root for the all subtrees. So you can understand all those terminology, whatever we discuss now with the help of this example. See, this is the structure example of the tree. We have the structure like this. We start our tree with a node. That node is called root node. That node is called root node. With which node you start the tree, that node is called root node. And that has left subtree, left side of the root node, right? So this is the left subtree and right hand side of the root node, right subtrees. So which is highlighted with the triangle. Okay, this is left subtree. And again, this is also a tree-like structures. For this subtree, this is the root node. And A is the root node for all these nodes. And here, this is subtree and this is also a subtree, this part. Subtree of A. Okay. And in this subtree, this is a parent node. In this subtree, this is a parent node. And D, E, F are child nodes of B node. D, E, F are child nodes of B node. And in the same level, what are the nodes we have at the same level? BC, same level is same, right? Second level. This is level 1 and level 2. These B and C are called siblings. B and C are called siblings. The nodes, whatever we have at the same level, are called siblings. And these are non-empty nodes, right? Because still they have some child nodes. That's why those are called non-empty nodes. And whatever the lines we are using to connect these nodes, those lines are called edges. The connected lines, whatever we are using to connect, these lines are called edges. And the nodes doesn't have child nodes. A node that doesn't have any child node is called leaf node. So in this tree, G is a leaf node, H is a leaf node, F is a leaf node, and D is also a leaf node because those nodes doesn't have any child nodes. That's why those nodes are called leaf nodes. Okay. So let me repeat the terminology. The starting node is root node. The connected lines are called edges. Non-empty nodes, these are called subtrees. Okay. Part of the tree, left side, right side, create another subtrees. This is another subtree. And the same level nodes are called siblings, and these are called child nodes. D, E, F are child nodes for B, G is a child node for C, C is a child node for A, and so on. And the nodes without child nodes are called leaf nodes. Clear, I hope? Now see, the root node is the topmost node, as we have seen just now. The root node is the topmost node in the tree hierarchy. In other words, the root node is the one that doesn't have any parent, obviously, right? So this is the root node, it doesn't have any parent. Okay. Suppose C node has a parent. C node parent is A. B node has a parent. B parent is A. But A doesn't have any parent because this is the starting point. It doesn't have any parent. So the root node is the node that doesn't have any parent. In the previous structure, we observed that. Node number one is the root node of the tree, right? Root A, that is node A, is the root node in this structure. If a node is directly linked to some other node, it would be called parent-child relationship. So in this example, the root node is directly connected with B and C, directly connected with B and C. This is called parent-child relationship. A is parent to B and C also. Okay. Then child node, root node is clear now. Root node is a node which doesn't have parent node, or you can say like root node is the node that is the topmost node in the tree hierarchy. To our right. Next child node. If the node is descendant of any node, then that node is known as child node. So in this example, B is the descendant node for A node. D node is the descendant node for the B node. E node is the descendant node for the B node. Like that, all these are called child nodes. G is the child node for C. C is the child node for A. H is the child node for E. Okay. If the node is a descendant for any node, then the node is known as child node. Then parent node. If the node contains any subnodes, then that node is said to be parent of the subnode. If any node have subnodes, then that node has parent node. If we observe B is a parent node because it has the subnodes directly D, E, F. D, E, F are subnodes for the B node. That's why B node is a parent node for D, E, F. Okay. Next. Sibling. The nodes that have the same parent are known as siblings. See, B and C are called siblings because B and C parent is A. The nodes whose parent is same are called siblings. The nodes that have the same parent are known as siblings. So in this B and C only siblings. EF are not siblings. Okay. D, EF are siblings. Okay. But FG are not siblings. F parent is B, G parent is C. So F, G are not siblings. We can say D, E, F are also siblings. Okay. Because D and E, F parent is B only. Like that. Leaf node. The node of the tree which doesn't have any child node is called leaf node. A leaf node is a bottommost node of the tree in the hierarchy. There can be any number of the leaf nodes present in a general tree. Leaf node can also be called external nodes. In this, these are the leaf nodes. A node which doesn't have child nodes. These are also called external nodes. Any tree contain any number of the leaf nodes. Okay, these nodes doesn't contain any child nodes. D, H, F, G. These are called leaf nodes. E is not a leaf node because it has one child node H. That's why D, H, F, G are leaf nodes. Internal nodes. A node has at least one child node known as internal node. Leaf node is known as external node, na? Just now we covered. Other than the leaf nodes, if any node has at least one child, for example, C, it has only one child. So this is called internal node. E has only one child. This is also internal node. F is not internal node. This is external node because it doesn't have any child node. G is also external node because it doesn't have any child node. H is also external node because it doesn't have any child node. D is also external node. But B is also called internal node because it has child nodes. At least if any node has one child node, that is called internal node. In this case, B has D, E, F, three child nodes. That is also valid, at least one child. Okay. So here B is internal node, E is also internal node, C is also internal node. Ancestor node. An ancestor of a node is any predecessor node on the path from the root to the node. The root node doesn't have any ancestors because tree starts with root node only. There are no ancestors are there for the root node. For example, so ancestors for the D. Ancestors for the D is B. Okay. In the same edge up to the root node, whatever the nodes available, those are called ancestors. For example, ancestor node for H, E, B. Ancestor node for G is C. Okay. Of course, A is also ancestor. Descendant, the immediate successor of a given node is known as descendant of a node. So immediate successor. Next node. So G is the descendant for the C. H is the descendant for E. Like that. Then let me discuss about the other term level. What is level? Levels of a node represents the number of the connections between the node and the root. How many connections? Connection means edges, connecting lines. Okay. How many number of the connections are there for a particular node? That node level is that number of the connections. If the root node is at level 0, okay, its next node is at level 1 and its grandchild is at level 2 and so on. See this? So if this is a level 0, so these are called level 1 nodes, BC, okay, BC and D, E, F, G. These are called level 2. So we have two connections now, two connections for these nodes. For F also we have two connections. Observe. For D also we have two connections. For D, for example, D, how many connections we have from D node to root node? Two connections. So that's why this is level 2 nodes. This is level 3. It has three connections now from H to root node. One, two, three. Three nodes, three connections, three edges. So that's why this belongs to level 3. This is about level. So we can define level of a node represents the number of the connections between that node and the root node. If node has no children, it is called leaves or external nodes or leaf nodes. We covered that. Nodes which are not leaves are called internal nodes. Internal nodes have at least one child node. Already we covered this point also. A tree can be empty with no nodes, or a tree consists of one node called root node. Okay. If we have only single node, that is also called as a tree. A tree with single node, that is root node. And a tree can be empty also without any nodes. Next term is depth. What is depth? Depth of a node. While talking about the height, it locates a node at the bottom, where for depth it is located at top, which is root level, and therefore we call it a depth of a node. For example, take a node B. What is the depth of the B? For that, we need to count how many edges between this node B and the root node. How many edges we have from this node to root node? Only one. That's why the depth of B is 1. So the same thing will be happen to the C also. So same level nodes contain the same depth. Next. For example, what is the depth of G? How many edges we have from this node to root node? 1, 2. Two nodes. Sorry, two edges. Okay, two connection lines. That's why the depth of G is 2. Then depth of K comma L are 3. Because how many edges we have from K to root node? 1, 1, 2, 3. 3 edges from K to root node. So the depth is 3 for the K and L also. So this is about depth. Next, height. The height of a tree is length of the longest path. Longest path means in simple terms, number of the edges from a node to leaf node, from a particular node to leaf node in that particular branch. For example, take root node 1. What is the height of this root node means? Select the longest path from this root node. See, longest path is 1 to 4, 4 to 60, 60 to 20. This is the longest path, right? How many edges we have? This is the leaf node. You can stop here. 3. So that's why height of 1 is 3. For example, can we write what is the height of 4? Draw a longest path from this node to leaf node. So if you consider 4 to 70, this is only one edge we have. This is not a longest path. You can say that this is the longest path, 4 to 60, 60 to 20 or 60 to 10, 2 or same. You can take any path because number of the edges involved in this path is 2 or 4 to 60, 60 to 10 also 2 edges. That's why the node 4 height is 2. What is the height of 0? 10 because this is the leaf node. We cannot draw or we don't have any a particular path from this node again because this is the leaf node only doesn't have any child nodes. All leaf nodes height is 0 only. Okay, all leaf nodes height is 0. These are called leaf nodes or external nodes. A node doesn't have any child nodes. That node is called leaf node, as we covered just now. Next, forests. A forest can be defined as the set of disjoint trees, a set of disjoint trees which can be obtained by deleting the root node and the edges which connects root node to the first level. Okay, in simple terms, if we remove the edges, what are the edges we use to connect the root node to the next level nodes? Then we can get some disjoint trees. Those are called forests. Let me give an example. Let us say this is our tree. Okay. And this is root node. Okay. A top level node in the tree hierarchy. Or a tree doesn't have any parent node. A node which doesn't have any parent node is called root node. We need to observe these edges. We need to delete these edges. If you delete these edges, if you disconnect these edges, you can observe you will get this tree, this subtree, right? This one. This is called forest. This is the definition. And this one more forest is C. And right side DGH. So this is one more forest. Let me repeat the definition again. Forest can be defined as the set of disjoint trees which can be obtained by deleting the root node and the edges which connects the root node. Okay, we are going to remove root node and which connects the root node directly. And remaining disjoint nodes, this one, and this one, are called forests. We have 3 forests by using this general trick. Next, we have different type of the trees in data structures concept. One of the types of the tree is binary tree. Binary tree is a special type of the data structure. In binary tree, every node can have, observe carefully, every node can have a maximum of two children, which are known as left child and right child. Every node in a tree, in a binary tree, we have the nodes, and every node can have, means that may or may not have. Maximum, they may have two nodes. Nothing but we can say that that may have one node or two nodes, one child or two childs. Okay. That type of the tree is called binary tree. For example, this is a binary tree. How can we say that this is a binary tree? Every node contain maximum of two children. See, node A, root node, it contains how many children? Two children. Maximum two children only. Suppose if we have one more children like this, D. This is not a binary tree. Okay. Maximum every node contains two children only. Then only that should be called as binary tree. Maximum two. Now, coming to the B, is it following that rule? It has only one children, D. Yes, valid, one or two. This has only one children. That is also valid. C, it has only one children. This is also valid. E contains two children. This is also valid. One or two. Every node must contain one or two children. That's it. Okay. That type of the tree is called binary tree. Now coming to the implementation of the binary tree. There are two types of the representation of binary tree. First one is linked list representation. So in this representation, the binary tree is stored in the memory in the form of linked list. This already we covered linked list now. So the tree is stored in the form of the linked list where the number of the nodes are stored at a non-contiguous memory location. This is the important part. Every node is stored in memory in the non-contiguous order and linked together by the inheriting parent-child relationship like a tree. With help of the pointers, with help of the pointers from parent to child, they are connected. But they are not stored in sequential order in the memory. Every node contains three parts. In this representation, the binary tree in linked list representation, every node contains three parts. Pointer to the left node, data element, middle one, pointer to the right node, right one. Okay. Each binary tree has a root pointer which points to the root node of the binary tree. We know that already, right? In an empty binary tree, the root pointer will point to null. Okay, that doesn't pointing anything. That is an empty binary tree. See this, the representation with the linked list. As we said, every node contains three parts. The left part contains the reference to the child node. The right parts contains the reference pointer or address of the right child. And if any node doesn't contain any left child, right child, that is represented with cross mark. For the C, there are no cross, nothing but it has some address here. That address is D's address. This address is address of the D. And here also right side, it has some address. That is the address of E node address. And here D and E are leaf nodes. D and E are leaf nodes. So those doesn't have any left or right nodes or left or right childrens. That's why the reference column is filled with null. In the representation, we can write cross mark. Okay, it represents actually null. It is not pointing any child. So a tree is seen as a collection of the nodes where each node contains three parts: left pointer, data element, and right pointer. Left pointer stores the address of the left child, while the right pointer stores the address of the right child. The leaf node contains null in its left and right pointers. Okay, those points we covered here. So in the memory, how the memory allocation for binary trees using linked list. So the memory allocation will be like this: left pointer, right pointer, data. So suppose it is a node, it has some address of left node, it has the address of right node. For example, E node, E doesn't have the right node, E doesn't have the left node, that is indicated with -1. So like this, we can represent the memory allocation of binary tree using linked list representation. So this image shows about the how memory will be allocated for the binary tree by using linked representation. There is a special pointer maintained in the memory which points to the root node of the tree. Every node in the tree contains the address of its left and right child. Leaf node contains null in its left and right pointers. Okay. Next topic is binary tree traversal. Very, very important point. What is binary tree traversal? Binary tree traversing is a process of accessing every node. Process of accessing every node of the tree and exactly once. In simple terms, we need to access each and every node exactly once. This is called traversal. Binary tree traversing is a process of accessing every node of the tree and exactly once. A tree is defined in a recursive manner. Binary tree traversal also defined recursively. Nothing but we can apply the same definition recursively while visiting each and every node. There are three techniques of the traversal. Those are pre-order traversal, post-order traversal, in-order traversal. Okay. Traversing is visiting each and every node exactly once. And we have three types of the traversing techniques, tree traversal techniques. Those are pre-order traversal, post-order traversal, in-order traversal. Now, what is pre-order traversal? The algorithm for the pre-order traversal is start from the root node. Start from the root node. Generally, we are going to visit the nodes like this. Root node, RT means root node, left node, and right node. This is root. So see the algorithm. Start from the root node, then go to the left subtree, then go to the right subtree. So this is the algorithm for the pre-order traversal. For example, we have a sample binary tree like this. So if we want to access all the nodes where I want to use pre-order traversal, then how the method will be? First, we need to visit root node as per the algorithm. And what is the left subtree it has? This is left subtree, right? And apply the same rule for the left subtree also. What is the same rule again? In that left subtree also, visit the root node first. What is the root node here? B. Okay. After that, go to the right node for the root node. So this is first one, root left, right. A, B, C. A, B, C. Right? Now, this is over. Coming to this again. Next level. D, E, F, G, H. When you visit D, root node. Okay? Root node first. Left node of this E, right node of this F. Left node, right node. Right? And coming to this GH. So there are no childrens. Directly you can visit GH. Okay. The following steps can be defined the flow of the pre-order traversal. A plus B, B plus pre-order on the D. So finally, we are getting the order traversal like A, B, C, D, E, F, G, H. And if we select post order traversal, the simple formula you can understand is post means left, right, then root node. Root node. Post means root node will come at last. LR root node. Left, right, and last you need to visit root node. This is the formula. See algorithm. Start from the left subtree. Okay, last leaf. And then go to the right subtree. Then go to the root node. See the same tree. Left subtree is B, D, E, F now. And right subtree is C, G, H. What is the root? A. Now, as per the formula, we need to go through the L, left subtree. In the left subtree, we have B, D, E, F. Okay. So in the same way, we need to go for L, R root. There is no L and there is R. Okay. So E until reach the leaf node, we must go through it. Okay. Last leaf. Observe here. Last leaf. So what is the last leaf here? E. So E must be visited first. And left, right, F. Then root node D. E, F, D. Left, right, root node. One minute. Okay, right. Next, BGH. Okay, BGH. After completing of right node. Root node, na? Root node for this is B. Then again right. G, H. Okay, left, right, root node. Apply the same formula at each and every node. Finally, you will get E, F, D, B, G, H, C, A. This is post-order traversal. Next. Right. In-order traversal. The simple formula you can remember. In order is L or in. In between we have root node. Okay, in. In between left and right subtree, we need to visit root node. This is the formula. This is the algorithm. What we are following. See the algorithm for in-order traversal. Start from left subtree, then visit the root node, then go to the right subtree. Okay. See the example again. Same binary tree we are taking. In that left subtree, root node, right subtree, we are representing first. In order is left, root, right. This is the algorithm. And coming to the left, same left, right, left, root, right. So B left. Okay. B is left. E is left. D is right. Left is completed now, then right. Root node for the E is D na. So root. Root node for the E is D. So write the root node. Left root is completed. Left root node is completed. Then right node. What is the right node? F. Then write F. Then again this part is over. And the next root node we have now, write it because single node. And this one, left, root, right. Left is G, root is C, right is H, G, C, H. So finally, this is the order in which order we need to traverse in the binary tree if we follow in order traverse. Right? Left subtree, root node, right subtree. Next, as we covered, we have different types of the trees. We covered binary tree and a different type of the travels in the binary tree. Next type of the tree is binary search tree. Binary search tree. Binary search tree is a binary tree which has a special property called BST. BST is nothing but searching. BST, binary search tree. For all the nodes A and B, if B belongs to the left subtree of A, the key at B less than the key at A. And second rule is, if B belongs to the right subtree of A, the key at B is greater than the key at A. Very simple. So if we have a root node and AB, root node, this is A, this is B, let us say. Whatever the values we have at the left subtree must be less than the root value. Whatever the values we have at the right subtree, those must be greater than the root value. So this is the rule about the binary search tree. See the definition. Binary search tree is a binary tree. What does it mean? Like maximum that must contain two nodes only. We must follow that rule also, because binary search tree is also a binary tree first. After that, binary tree is a binary tree where each node contains only smaller values in its left subtree. The smaller values than the root nodes must be exist at left side only, left subtree only, and only larger values in its right subtree. That is called binary search tree. See, suppose I have a binary search tree. Let us check whether we are following the rules or not. See, the root node is 50. If you observe the subtree value 30, 20, 15, 25, all the subtree values are less than 50. 30, 20, 15, 25. If you observe the right subtree values, all are greater than the 50. 80, 75, 100, 68. So in such a way, we need to arrange the values. So that is the definition of binary search tree. Point one. Next. Again, if you come to the any subtrees, this is one subtree now. It doesn't have right side. So it has left value, and the left value must be less than the root node for this subtree. For this subtree, root node is 30 na? For this subtree only. 30 is root node. So the left side values must be less than the 30. So that is 20. So if you write 40 here, that becomes invalid. Okay, the left subtree of the 30 should not have the greater value than 30. If you write 40, it will not consider as a binary search tree. After that, consider this is also a subtree. No? What is the root value in this subtree? 20. What is the left subtree or left node? That value must be less than root node. 15. Less than 10 years. True. Right node must be greater than the root node. 25. Greater than 20 years. Like that, at each and every node, the formula must be satisfied. Coming to the right side subtree, 50. So 80 value is greater than the 50 because it has a right, it is a right subtree for the 50. And if you consider this is a subtree, 80 is the root node, and we have the left subtree, that value must be less than 80. So we are writing 75. Here you must remember, when we are writing the value of left subtree of the 80, that must be less than 75 and greater than 50. If you write 10 here, that becomes invalid. Why? Of course, the 10 is the less value than the 80, but all the left subtree values must be greater than 50. We are not following that. So that's why that value must be less than 80, greater than 50. Coming to the right hand side, that value must be greater than 80. Obviously, if the value is greater than 80, that will be greater than 50 also, right? Then, like this, you can apply the same formula at each and every level and you can create the binary search tree. So this is about binary search tree. So in our today's session, we cover what is a tree and the important terminology about the tree. A tree is a non-linear data structure and that contains zero or more nodes. What is a root node, left child, right child, and child node, parent node, internal and external nodes, leaf nodes, and what is level, what is depth, what is height. We cover all these basic terminology about the trees concept. After that, we have started the discussion about types of the trees. As part of that, we covered binary tree. A binary tree is a tree which has at most two children. And after that, we have seen binary tree traversals. Traversal is nothing but visiting all the nodes at once. We have three types of the traversal: pre, post, in, pre-order, in order, post-order. Then finally, we discussed binary search tree. In the binary search tree, the formula is all the less values should be present at the left-hand side of the root node and the larger values should be present at the right-hand side of the root node. And that should be recursively applied for the all levels, all the subtrees. So these are the points we cover as part of today's session. In the next session, we are going to see the implementation of binary tree and binary search tree. And we are going to see uh, some more different types of the binary trees also. Okay. So that's it for today's session. Thank you.